Did you get it?
Yeah.
All right, I will begin. Heavenly Father, we thank you for this day again, Lord. I thank you for these students. Just ask you to bless this class and help us as we prepare for the inevitable CFA. Amen. All right. We still have a few hours of peace. All right. So, what problem was that? So number 33, yes, number 33 is really two problems masquerading as one. Sorry. I should have made like part A, part B, but I was too lazy. My bad. Hey, well, we have a couple minutes. We can talk about, oh, thank you. Everybody, this find its way to everybody? All right. Anyone who's not here, say something now. I can also prove that I know the name of everyone because I can't name one person I don't know the name of. So it's neat how that works. But I digress. Any questions about the mission? I can just give you a kind of a quick hint if you have a question. It's due tomorrow.
Number 42.
Number 42. I steal yours, thanks. Oh, so remember in one of the daily quizzes, we let big F of xy equal to x. We looked at the limit as h goes to 0, and we studied how to prove the partial x, partial y was 0 from the limit definition. Look back at that. It's exactly that.
That was last Friday.
What's that?
Last Friday.
Last Friday's daily quiz was actually this, yeah.
What exactly are you wanting on 32?
Oh, so by the way, before I forget, just a random comment. Total differential is really, I mean, to make it careful, that ties into the general derivatives discussion I had. All right, but for the sake of this course and your understanding, just think of it formally. It's something we can do. And, you know, so if I have a function of x and y, then the total differential is by definition partial f, partial x dx plus partial f, partial y dy. So like, for example, if we had f of xy equal to, I don't know, x cubed plus e to the y, then we'd get that df was 3x squared dx plus e to the y dy, for example. You'll also encounter this kind of language in engineering where you might not even say what your function is of. You might just have like an expression. You can still take the total differential of expressions. For example, if I was to take the total differential of alpha, beta, gamma cubed, well, what would that be? That would be, you do partial alpha of the thing, d alpha, plus partial beta. So, you know, it's just common custom to treat the variables which appear as independent and just proceed formally, essentially. So this would be beta gamma cubed d alpha plus alpha gamma cubed d beta plus 3 alpha beta gamma squared d gamma. So this notion of a total differential, it's a very robust idea. It just means you take partial derivatives of each variable which appears and multiply them by the differential. You say, well, what's a differential? Don't ask me that. I mean, this is a differential form. So a differential form is a, well, it's an expression that involves a linear combination of differentials. If you really want me to give you an honest answer, we can take it and we can evaluate, for example, the df. I can take df on h comma k, like that. And this will then be equal to h times partial f partial x plus k times partial f partial y. So it's actually, this is that differential I talked about yesterday in the general derivative. And it gives us a method to approximate the change in the function at the point in terms of the partial derivatives and the local linear approximation. So that's what the differential is for. It's actually where the rubber hits the road, where you approximate, where you can approximate the change in the function at the point. But on the other hand, there is a sense in which this just exists formally as something you can do. We don't have to have this discussion, and we can still take the total differential. It's very simple. You take partial derivatives and multiply by dx and dy as appropriate. There's a problem in your homework which is like this. Don't make more of it than it is what I'm trying to tell you. You just partial differentiate and multiply by differentials and work with it. Yep.
Yeah, differential is the second one. That's just what it is.
Right.
We'll continue evaluating them.
Yeah, there's nothing more to do. That's it. There is a well-described procedure to use the total differential to calculate or approximate the change in the function near a point. There are things we can do with it, but I didn't ask about that. Yeah. So there was a question asked about 32, was it? I didn't address that yet. I mean, 32, we should just draw pictures and, proceed from drawing pictures, basically. Here, for example, if I had, this was my set S. Suppose this was the set S, right? So this might be x, y, such that, I don't know, the absolute value of x is less than 1. The absolute value of y is less than or equal to 1. Then this line up here would actually be y equals to 1. This would be y equals to minus 1. This would be x equals to 1. This would be x equals to minus 1. And here is a typical point which satisfies those inequalities, right? So the interior point, just any point inside the box where I can take that point and I can draw a little open disk around it, that would make this an interior point. There are two kinds of boundary points. What is a boundary point? A boundary point is a point which is, if you draw any little open disk around that point, there are points inside and outside. That makes it a boundary point. So like this is a boundary point, right? Any open disk I draw like this, we got points out and we got points in, right? So that's a boundary point. There's also a boundary point down here, right? So here's out, this is in. No matter what size disk I draw there, there's always points out and in. Those are boundary points. One of those is in the set, one of those is not. You tell me which. Let's call this P1, I'll call this P2. Which one is, so if this is my, S, P2 is what? Not an element of S, right? What's P1 is what? Is an element of S, in fact. If a set contains all of its boundary points, it's said to be a closed set. So while the shape of that problem is different, that should be right. Yeah. So really, you draw a picture, you draw some little disks, you write a couple sentences. That's the solution there. It's not that it shouldn't be that complicated. Right? There's no like working out inequalities or anything, Math 431-ish. You guys will take real analysis in due time, right? You guys are all taking real analysis, right? No, just kidding. You're not all math majors, right? So that would be really strange. Like, yeah, for my upper level technical elective in engineering, I chose the hardest senior level math course. Yeah, I'll pick that one. Right? No.
I'll stick with my piano.
Opinions vary whether or not that's harder than Math 4 abstract, but I don't know. To me, real analysis was harder than abstract algebra, but whatever. But that's because I have certain weaknesses with inequalities. I tend to think of things left, right, and juxtapose them. It's very bad for inequalities. Harmless for equalities, right? If I forget which is the left-hand side and the right-hand side of an equation, does it hurt me? Not too much, right? But for an inequality, you forget which is the left and which is the right. It's all over. Other questions about the mission? All right. So today I wanted to talk to you guys about the concept of the tangent plane. And we may end up talking about, you know, the chain rule, but I'm going to let that come up organically. So the discussion for today, so we talked about curves, level curves the other day, right? So today we're going to talk about surfaces. And more than that, surfaces and tangent planes. So what's a tangent plane? Let me draw a picture, roughly speaking. So a surface is some kind of, I don't know, some kind of curvy thing. It might have some kind of hole in it, who knows, whatever. Could be a donut, you know. Donuts. Let's see here. Sorry. I may have gone to Dunkin' Donuts before class. So, you know, surface, we could call it M, whatever. And if you pick a point, right, the surface is generally curved. And so if we pick a point on the surface, right, like that, and we study all curves that go through that point, all right? So all curves that go through the point, but they're on the surface as well, all right? So think about that. You know, I have this curve, that curve, that curve, that curve. They're all going, they're supposed to go through the same point, all going through the same point, all right? And then you can do what? You can take these curves, and we know how to do what with curves. We can look at their tangent vectors at that point, right? And we can study the tangents to all those curves, all right? And so those tangent vectors, right, if this point is actually a point, you know, I've got too many arrows, but the point is, if you look at all those tangent vectors from all those different curves, if they actually all fall in a single plane, then the function, well, the surface is said to be differentiable. Or you could, if it's nicer than that, you might even say it's smooth. The point is, if you can look at all these curves and they all fall in some plane, then that plane is said to be the tangent plane to the surface at that point. So this plane where all the tangent vectors fit into is the so-called, if this point is P, this would be the tangent space at P to M. All right, lived a good life, but I think it's over. Curses. I missed Ian. Let's see here. So the question is, it's a tangent plane, right? So how do you want to describe a plane in 3 dimensions? We're going to work in 3 dimensions here for a while. Parameterization of 2 variables? No. That's not how we like to talk about planes. What's a plane?
The cross product between.
Now you're getting into the weeds, cross product. No. That's how we calculate the plane. But what is the plane? How do we describe a plane?
Base point and normal vector.
Base point and normal vector, right. So something like this, right? Right, so this would be the equation of the tangent plane, right? How do you find that, is the question, right? For a given surface. Oh well, missed him again. So the deeper question here, before I even ask that question really, is how do we describe a surface in 3 dimensions? How do you do that? Right? So I've told you before, but there are 2 ways to do it. We can either describe it parametrically with 2 parameters, or we can describe it by an equation, right? So, for example, M, let's pick on a specific one. Let's think about M being the sphere of radius r. I can describe that as an equation. It'd just be x squared plus y squared plus z squared equals to r squared, right? The solution set to this is the sphere, right, of radius r, centered at the origin, right? But I could also describe it parametrically, right? How would we describe this parametrically? How would you describe a sphere parametrically? Well, you do something like this. R of, let's say, phi and theta is r cosine theta sine phi, r sine theta sine phi, r cosine phi. Where did that come from? Yeah, I basically just froze out one of the spherical coordinates. I created this parameterization by setting the spherical radius rho equal to r. But this is a parameterization, right? And I would say 0 less than or equal to phi, less than or equal to pi, 0 less than or equal to theta, less than or equal to 2 pi. This covers the sphere. And so we have a kind of different situation than curves. Like curves in 3 dimensions, describing curves in 3 dimensions by 2 equations, it's kind of awkward, right? But parametrizing a curve in 3 dimensions, well, that's easy. We just need to give r of t, x of t, y of t, z of t. That's a path. That's been a very useful viewpoint for us. Surfaces, there's really less of a distinction between the usefulness of these different viewpoints. Like the parametric viewpoint is very natural because we can just write down a parameterization, and it's got a lot of advantages to describe the sphere. But a single equation in 3 variables also describes a surface, which is also a very simple and easy thing to wrap your mind around. Yeah.
Should that be r cosine theta sine cosine phi for the x section, or r cosine theta sine phi?
Okay, well, if I'm right, if we plug in these equations, they should work, right? So let's say this is x. Let's say this is y. Let's say this is z. Let's check if it's a parameterization, if it's legit, right? If it's legit, it should satisfy the equation of the sphere, does it? X squared is r squared cosine squared theta sine squared phi. And then y is r squared sine squared theta sine squared phi. And then z is r squared cosine squared phi. Does this work? Does this simplify down to r squared? It does, because you notice that this guy and this guy, we can factor out a common sine squared phi, right? So this, because cosine squared theta plus sine squared theta is 1, collapses down to r squared sine squared phi plus r squared cosine squared phi, which of course then is r squared, yeah. So it works. This is not surprising though, because it goes back to their spherical coordinate system. We had this was rho, right? This angle was theta. This angle was phi. So this gave us that the z was rho cosine phi. This down here was rho sine phi. So then when you look at the triangle in the xy plane, this down here, that's the hypotenuse opposite rho sine phi hypotenuse times sine opposite the theta. Over here, rho sine phi, the hypotenuse, times cosine, because it's the adjacent to the angle. So these are not things to memorize. They are things to understand. And you can understand them. You just have to invest some time in these pictures. That parameterization is simply coming from setting rho equal to r. We're just freezing out the spherical radius. We're fixing it. And that gives us a way to parameterize a sphere in terms of the spherical coordinates, phi and theta. Now, not every surface comes with some sort of like natural parameterization in terms of some sort of, pre-existing coordinate system, but sometimes they do. Spheres, cylinders, cones, half-planes. These all appear as level curves of curved linear coordinate systems, which are commonly discussed. All right, so we got 2 ways to describe a surface, parametrically or as an equation. So I want to describe to you how we find the tangent plane to either viewpoint. All right? Let's start with surface. Let's start with level surface. Level surface. It's just what it sounds like. And now I said level surface in the class where we talked about level curves by accident, because I had it on my brain. I was watching the video. I was like, oh, I said level surface. I meant to say level curve there. I don't know if you guys noticed or not, but no one corrected me. So a level surface, something like f of x, y, z, equal to a constant. Right? So geometrically, how's the equation of the tangent plane? Tangent. What's a vector? What's a vector which is tangent to the? Well, let me just show you a calculation. Suppose that we have f of r of t equals to c for all t. So what does that mean? If you want to think about it geometrically, what that means is we've got some surface, right? F of x, y, z equal to k, c rather. And that r of t is a path, right? So if we plug the path into the level function and it gives us c, what's that mean? That means that the path lies on the surface. Like if I gave you a parameterization for some curve such that x squared plus y squared plus z squared equals to r squared, that would tell you that the path is on the sphere. You know, it could be something crazy. This path could do like, I don't know, it could be all kinds of crazy junk. But if the parametric equations for the path, the x of t, the y of t, the z of t, if when you square them and add them together, you get r squared, well, it's on the sphere. So mathematically, that's what it means for the path to be on the sphere. It means that when we plug in the path to the level equation, it works. So geometrically, that's the path. Here's a particular point, r of t on the path. Yeah? Did you have a question? No, okay. So guess what? There's a chain rule. If we differentiate with respect to time this equation, what happens? The chain rule, right, which I would derive in a different course, but I'll just state for you here, is the gradient of f in the three-dimensional sense of r of t dotted with dr dt, well, that's equal to the derivative with respect to time of the constant. What's that? Well, 0, right? Derivative of the constant 0. So guess what? If you have a curve on a level surface, that curve has tangents which must do what? They must be perpendicular to the gradient, to that surface, right? So if I was to draw the gradient into the surface, it would have to look like this, right? It's perpendicular to the tangent. The tangent looks like, well, it's tangent to the curve, right? So tangent looks something like this. So what happens as you toggle through different possible curves through a given point on the surface? What happens? Every possible tangent is perpendicular to what vector? I mean, I did that for one curve, but I can just as well do it for other curves through the point, right? I mean, I didn't really tell you which curve it was, but if I went through another one, it would still be the case that, you know, if I had f of r2 of t equal to c, right? Then, and I said this one was 1. Well, then that one would also be tangent to that same gradient vector, right? So you see the gradient vector is playing the role exactly what we want. It's playing the role of the normal to the tangent plane, right? It is the thing that's perpendicular to the tangents to all possible curves through the point. This is wonderful. So to calculate the normal vector to the tangent plane, all we have to do is what? Normal to tangent plane at, say, r of t naught, you know, in the surface M is given by what? Let me call this point P, just to give it a name. And here M, I'm saying M is equal to what? Specifically, it's all x, y, and z, such that f of x, y, z equals to c. I'm saying M is the level surface defined by level function f. This little derivation shows you that the gradient vector at the point P is the normal to the tangent plane. So simply gradient of f at the point P. Oh man, that is a sad, sad marker. Just like I planned it. There. That's right. Next time I'll actually hit him. I should get Nerf guns. Just bring them to class and like rant. Have you ever had a professor do this? Like, oh yeah? It's been done, huh? What kind of class? Oh, you heard about it, huh? Oh, a different school. Ah, high school? Yeah. Huh. I think in high school I would go with like maybe a squirt gun. Yeah, I think so. Something like that. Maybe, well, yeah. Not make it worse. All right. Okay, so example. Check this out. What surface do we already know about in 3 dimensions? How about this one? If we have surface AX plus BY plus CZ equals to D, right? So this is a level surface, isn't it, for a given ABCD? So this is my f of xy, right? F of xyz. What's the gradient in the 3-dimensional sense of that function? Partial xf, partial yf, right? Partial zf. What's that? A, B, C. So apparently the normal vector to the tangent plane to a plane is just the normal vector to the plane. In other words, a tangent plane, a plane is its own tangent plane. If you'd like to find the best planar approximation to a tangent plane, to a plane, it's the plane itself. Find a linear approximation to a plane. You're looking at it, you know? So this whole construction, this whole idea kind of just collapses down. That is, of course, the normal vector to the plane everywhere. I mean, we should expect that, right? What if we had f of xyz equal to x squared plus y cubed plus, z to the 4th, and suppose that's equal to, I don't know, 42, right? Can you guys find for me a point on this level surface? Make me do all the work. You guys find a point on that surface. Put you guys to work. What's that? 0, 0 squared root 42. So I'm hearing a square root of 42, 0, 0 is my point.
You could do a cube root in the y position or fourth root in the z position.
I mean, we can work with that point. It's just not especially exciting. Oh, what's my second point? 0? Oh, you got... I don't know why I'm listening to you. Let's see here. Fine. How about this? One more point. 1, what's that get me? Yeah, 4th root of 42. Oh, 40. Yeah, thank you. Anyway, let me stop trying to think of something nice. Anyway, these are 3 points on the surface. Let's find the equation of the tangent plane at each one of these points. All right? So the gradient vector field is what? nabla f at the point x, y, z, that's easy enough to calculate. It is 2x, 3y squared, 4z cubed, right? So let's look at my point P, Q, and I'll call this one Pac-Man. All right, so point P, we've got the gradient of f at P is what? 2 times the square root of 42, right? 0, 0. So what's the equation of the tangent plane then? We have 2 times the square root of 42 times x minus the square root of 42 equal to 0. So there you go, equation of the tangent plane. Also known as x equals to the square root of 42 is the tangent plane. It's not an especially exciting tangent plane, but it is a tangent plane. So there you go, equation of the tangent plane. This is the equation of the tangent plane at P2. Oh, I didn't give this thing a name. Let me call it S for surface. So, I mean, if you want me to be mathy here for a second, S is equal to the inverse image under F of 42, for what it's worth. S is the level set. The level 42 level set for that F, big F. Okay, Q. What we got for Q? Gradient of F at Q is what? You guys, 0, 3 times the cube root of 42, quantity squared, right? Which then implies we have what? Our equation is 3 times 42 to the 2/3 power y minus what? Oh yeah, cube root of 42 equal to 0. Of course, again, this is a kind of boring tangent plane because I gave you guys too much control over my lecture at the moment. All right. Pac-Man, someday I'll learn. Pac-Man, gradient of f at Pac-Man. Finally, something exciting here. So 2, 3, and then 4 times what? 4 times 40 to the what? Z cubed. So yeah, 3/4 power. Whatever that is, don't really care. So this gives me 2 times x minus 1 plus 3 times y minus 1, and then plus 4 times 40 to the 3/4 power times z minus the 4th root of 40 equals to 0. Finally, an example which actually you can appreciate. You're like, well, you're the one that asked us for points. That's true. I did open the door. It's my own stupidity.
Well, we typically ask you for points, so it's nice to change.
You typically ask me for points. That's a very nice turn of phrase there, Nathaniel. All right. Anyway, so to find the tangent plane to a level surface, it's really quite simple. All you do is calculate the gradient vector field, plug in the point, that gives you the normal, and then once you have the normal, you have a base point, you can write the equation of the plane, right? Make sense? So, how would you find the tangent plane then? How would you describe the tangent plane from the other perspective? How would you find the tangent plane for a parametrized surface? How would that go? What's the difference? Let's look at a specific example. So oftentimes people use UV for the, the other viewpoint. So parametrized S typically given by something like R of, say, u and v. And you get three functions. You get x as a function of uv, you get y as a function of uv, you get z as a function of uv. All right? And let's talk about this for a little bit, because we haven't talked about it that much in here yet, and it's kind of a big part of this course, the study of parametrized surfaces. So essentially here we have the uv, the parameter domain, all right? And so you got some sort of, let's suppose for the sake of simplicity that we've got, say, u1 less than or equal to u less than or equal to u2, v1 less than or equal to v less than or equal to v2, just for the sake of discussion, right? In other words, I'm assuming that the parameterization has a rectangular domain. That doesn't have to be the case. Your parameters could be taken from something much weirder. This one has a rectangular domain. See, the u here is phi, and the v is theta, is the idea. So like u1 is 0, v1 is 0, u2 is pi, v2 is 2 pi, if we want to bridge the notational divide here. Anyway, you got some kind of, parameter domain here. All right? And then what this parameterization does is it pastes it. It basically glues this. It twists and morphs and glues it somewhere up into 3 dimensions. That's what the parameterization does. It takes this little, think of it as almost like a little rubber sheet, and it stretches it and bends it and pastes it over the surface you're interested in describing. This is a parameterization. Just like a parameterization of a curve, you could think of as taking the string, with t along it, and then just kind of pasting it over 3 dimensions and laying that string along the curve you're describing. Same idea. But now we have 2 dimensions to paste. And so the question is, if we pick a particular point here, right, a point P, and we want to describe the tangent plane at that point P in terms of the parametrized description, how should we do it? See, that point P is going to be mapped from some other point over here. Let's suppose, in particular, that R of u naught v naught is equal to P. And when we call it P naught, just to make all the knots go together. So here we go. So what we can do is we can take very special coordinate curves. We can take curves which are horizontal and vertical in the domain, in the parameter domain. So like this one, this curve like this, right? That has fixed what? There we have what? We've got u is free, right? U varies, right? But v is equal to what? In my picture, v is equal to v naught, right? So v naught is fixed, right? Now the parameterization does what? That puts it over here, and it gives it some kind of, maybe like this curve, right? This would be R of what? Of u being free and v naught being fixed, right? That's a typical point right here. We can also look at the vertical curve, right? Like this, through that point. See that? What's a typical point on this look like? Here we have u equal to u naught, and how about v? V is free to vary along that vertical curve, right? And so that green line would map over here to some kind of curve on the surface, like that. And a typical point on that green curve would have the form R of, well, u naught is fixed, right? And v is free to vary. Does that make sense? I mean, you might ask, why are you doing this, right? Well, what's my goal? My goal is to describe to you how we find the tangent plane to the surface from the parametric viewpoint. I can't just take the gradient like we did for the surface. I don't have a level function to work with, right? So I'm trying to describe with the calculus, with the formulas we have, how do we find the tangent plane? Okay, so what can we do? We can find the tangent vector for the blue curve, right? So if let me just give it a different name. Let me say alpha, basically alpha, let me call it R1. R1 of u, right, is R of u comma v naught, right? And I really should have used blue for that. Sorry. Bothering me. Or we could even use a t if that would make you guys feel better. It doesn't really matter. R of t, R1 of t is R of t comma v naught, right? So what's the tangent vector? dr1 dt, right? Would be d dt of R of t comma v naught, right? Yep.
Do you, but to find the or normal or whatever, do you find a tangent for both, then take the cross?
That is in fact where we're going. Yes, we're going to find the tangent to both curves. We take the cross product to get the normal. Yeah. Spoiler alert. Thanks a lot. Let's see here. So anyway, we can calculate this tangent vector, and we can also calculate that tangent vector. So in particular, getting to the point here, so that would be, but you know, the thing is, what this is at the point, good grief. So what is this? This is nothing more than partial r, partial what? I'm doing what? I'm changing u, holding v fixed, right? That is a partial derivative with respect to what? U, right? And I really shouldn't have done this t thing. I'm sorry. dr1 du. I'll fix it. I'm sorry, guys. Should have stuck to my guns. And then on the other hand, the R2, right? If we say R2 of v is R of u naught comma v, right? Well then dr2 dv, which of course would be the velocity vector field to the blue curve. Well, that's nothing more than d dv of r of u naught v. So we're holding u fixed and we're varying v. That's exactly what we mean by partial r, partial v. So long story short, we observe that partial r, partial u at the point u naught v naught, and partial r, partial v at the point u naught v naught are tangent vectors to S at R of u naught v naught. So yes, from a parametric perspective, what do we need to do to find the tangent plane? If we're just looking for a parameterization of the tangent plane, that's pretty easy to find from the parametric viewpoint, because this gives us two tangent vectors on the plane. We can build a parameterization of the tangent plane with these pretty easily. But if we want to find the equation of the tangent plane, starting with the parameterized viewpoint, we got some work to do. We take partial derivatives to find the tangent vectors, then we got to go through the usual song and dance to find the equation of the plane from two tangent vectors. Right? Let me actually work that out for a specific example. Okay? And not this example. This one hurts if you do it. Probably made that homework, right? So example. What example am I on? 3. All right. So let me do one. Hey, moved that away from the wall, didn't you? See what you did. Make me look bad. God, see what you're doing over there. Well, this one's worthless too. R of uv, let's say u, comma, u squared plus v squared, comma v. All right. What I want to do is I want to do two things, all right? I'm going to we'll pick a point on the surface that this is parametrizing, and we'll try to pick a somewhat interesting point. So let's say this parametrizes a surface, let's say S, all right? I want to find parameterization, a parametric and level surface, parametric description and equation description. I'm not very happy about my grammar at the moment. For the tangent plane at the point P to S, where P equals to what? Actually, I've learned my lesson. I'm not going to let you choose. I'm going to choose parameters 1 and 1. So if I choose the, u equals to, well, maybe let me do 1 and minus 1 so you can see the contrast a little bit better. So 1 comma minus 1, what points does that give me? I plug in u equals to 1, v equals to minus 1, I get 1, 2, minus 1. All right. So let's find tangent vectors. Let's find tangent vectors to that surface using what we just learned about the connection between the partial derivatives of the parameterization and the surface. So we got partial r, partial u. How does that work? By definition, guys, that is partial u, partial u of u squared plus v squared, and partial u of v. So what's partial v, partial u? V and u are independent, all right? So partial v, partial u is 0. So this works just like the x, y partial derivatives we've been doing up to this point. Same song and dance. Just think of u being like x and v being like y, and you should be okay. This works out to what? 1, 2u, and 0. Very good. Right? So by the way, sometimes people use this notation too. They'll say that this is r sub u. You'll see that notation sometimes, r sub u, for like the partial derivative of r with respect to u. That's analogous to like the f sub x notation for partial derivative of a function with respect to x. This is another notation you'll see in books sometimes. What's partial r, partial v? So we got partial v of u, partial v of u squared plus v squared, partial v of v, which is what? 0, 2v, and 1. And again, for what it's worth, that's also denoted r sub v. Or, while we're on this, parade of unnecessary notation, we can also denote them like this. Other notational choices. All right, so can you guys tell me, what is the tangent vector then at p equals to r of 1 comma minus 1 right? We have tangent vectors what? We have partial r, partial u at the point 1 comma minus 1 equal to what? And partial r, partial v at the point 1 comma minus 1 equal to what? So we just have to go back and evaluate this at u equals to 1 and v equals to minus 1, which gives me what? 1, 2, 0, right? So 1, 2, 0, that is tangent to the tangent plane. And then this guy, when I plug in 1 for u and minus 1 for v, I get 0, minus 2, 1. So just to emphasize what's going on, let me try to bring it together over here a little bit, draw a picture. We've got this, actually this is the tangent plane. I don't really know what the surface looks like. Actually, I do. It's a lie, I know. But I'm not telling you yet. This point here was the point P, which was, what did I just say it was? It was 1, 2, minus 1, right? And we just figured out we've got partial r, partial u of 1, 2, 0. And we've got this other vector, 0, minus 2, 1. These are tangent vectors, right? So if I wanted to find a parameterization for the tangent plane, and I know a base point to the plane as well, right? 1, 2, minus 1. So to let me call this plane P. Well, I have, sorry, excuse me, I have a different name for it. Tangent plane at the point P to the surface S, TPS. So the parameterization of TPS, what would we do? What we do is we do R of, let's say U. I mean, we could use U and V again if you wanted. I'll do that. R of UV, the base point, which was 1, 2, minus 1. And then you just do U times 1, 2, 0, plus V times 0, minus 2, 1. That, folks, is it. I mean, that is a parameterization of the tangent plane. So finding a parameterization of the tangent plane, given a parametric description of the surface, it's a piece of cake. Why is that a parameterization of the tangent plane? What does that formula mean? Maybe I shouldn't use U and V here. Maybe I should let me use S and T just to be different. Here, I'll use S and T. All right. So what does this mean, this formula that I just boxed? This first piece, where does that get you? Let me draw the plane again down here. So this point would be 1, 2, minus 1. And then we're adding S copies of the tangent vector 1, 2, 0. So that moves you like this over to this point. You know, this is S. So this point right here would be, 1, 2, minus 1 plus S times the first tangent vector. And then you're adding T copies of the other tangent vector. But the point is you're adding linear combinations of tangent vectors, right? And it's a plane, so that means you're staying on the plane. And as you let S and T vary over all possible values, that fills out the whole plane. That's a parameterization of the tangent plane. So there you go. That's my R of ST. These are T copies of the this guy. Yeah. Now we have to go back to Joshua's foreboding comment. To find the equation for the tangent plane, we need to find a normal to the tangent plane. We've got two tangent vectors. How do we find a perpendicular vector to those, which must be the normal? We take the cross product. Kind of a drag, but something we can do, right? So to do that, normal, we take what? We got 1, 2, 0 crossed with, what is it? 0, minus 2, 1. What's that give us? 2 minus 1 minus 2. Let me check that. Yeah, it's perpendicular to both. Therefore, 2 times x minus, what's my base point? 1, 2 minus 1. So x minus 1 minus 1 times y minus 2 minus 2 times z plus 1 equals to 0. There you go. This is the equation of the tangent plane at P through S. Right? So here's a question for you. If I give you a choice in the matter, if I say, I want you to describe the tangent plane to a surface, right? And I don't say you have to do the parametric description or the equation description, right? Which should you choose? What would be the lazier choice? The parameterization. Actually, the answer depends on how I've presented the surface to you. If the surface is presented as it's currently presented, you're right. Parameterization is the way to go. Because all we have to do is calculate the partial derivatives, plug in the point. Those are my tangent vectors. I build the parameterization like that. Done. On the other hand, what I didn't do, right, the thing I erased, I didn't find you a parameterization of the PQ and Pac-Man. I just wrote down the equations for those tangent planes, right? It would have been a pain to find parameterizations of those tangent planes. I would have had to gone back to earlier methods like pick 3 points on the plane, find tangent vectors on the plane, use those to build the parameterization, something like that. So if you're given a level surface description of a surface, it's much easier, of course, to find an equation to describe the tangent plane. But these are equivalent ways of describing the same geometric object, right? We want to learn how to go back and forth between these ideas. All right, so then I will then turn the next page, which is how would we describe this surface as a level surface? Could you tell me? What is this surface as a level surface? So let me suggest this. We can look at this surface, right? It's x equals to u, right? Y equals to what? U squared plus v squared. Z equals to v. To find the Cartesian equation for this surface, if such a thing is possible, is simply to eliminate u and v. We've got 3 equations and 5 variables, right? So this requires a certain amount of creativity. It's not like a cut and dried, oh, I remember when I learned how to do that in Algebra 2, you know? You're learning how to do the algebra now. But this particular problem kind of suggests an easy path. Let me write it over here. So we've got x equals to u, y equals to u squared plus v squared, z equals to v. Can you tell me how to eliminate u and v? This one's actually kind of easy. So you're like, put this one down in there and put this, like, so we get y equals to what? Y equals x squared plus z squared, right? Yeah.